cryptography, which is the public key. Public key cryptography and RSA. RSA is the most is one of the common methods of public key cryptography. There are other methods. So we'll talk about how public key works, how it is different from symmetric, what is RSA algorithm, and then we'll go into detail as to how you can optimize RSA. So public key was invented by Diffie and Hellman at Stanford. Interesting, because the money was made by RSA, which were at MIT. So somebody does the invention and somebody else makes the money. But anyway, so Diffie and Hellman at Stanford invented it, and their basically invention was that you need two keys. If you take the text, use first key to get a ciphertext, and then use the second key to get the plain text. So previously everybody was using one key. Same key for encryption and decryption. They said, if we do two keys, then something different can happen, as we'll see in this chapter. And the keys are interchangeable in the sense that you could use second key to encrypt, and then the first key can be used to decrypt. That is the second property. That either key can be used to encrypt. Whichever key you use to encrypt, the other key can be used to decrypt. And the third property is that one key is made public while the other is kept secret. So one key you can put it on your website and say, well, here's my public key, and then you will see how the people can use it to send the text to you, and then basically you only can decrypt it. The other is private, so that other one nobody knows. Sender knows only the public key of the receiver. So when you want to talk to somebody, you just need to know their public key, not the private key. Okay? So the next slide will explain how all this works. Well, not the next slide, maybe slide number 6. So you wait till slide number 6 to figure this out. Really bad. Maybe I should go to slide number 6 anyway. So when you want to send something, when A wants to send something to B, A takes the message and encrypts it with its private key. Okay? And then encrypts it with B's public key. You see, there are two locks. You put the message inside a box, and the lock here is private key of A. And you put inside another box, and the lock here is public key of B. Now A knows both of these. A knows its own private key. It knows if A knows B's public key. Right? So it can send this message. Now look at this message. Who can open this message? Who in the world can open this message? Only B can open, because B only has its private key. Nobody else, even A cannot open this once it is encrypted. I mean, it cannot, well, I mean, A knows that what is encrypted, so that's a different thing. But given this, nobody can decrypt it, and only B can decrypt it. Now, once B decrypts this part, can it open this lock? Because everybody knows the public key. So there are two things which happened here. Not only that nobody can open this, nobody can send this. So when B gets this one and uses the A's public key to open it, then it says, I know this is sent by A, nobody else could send this one. So there is an authentication also. So there is a privacy and authentication. It is guaranteed that it was sent by A, and it is guaranteed that nobody else can read it. Okay? And so that's the public key method, and so that's why we use it so much. Now let's go back to this slide number 4 that we skipped. So RSA method is the simplest, not simplest, is one of the methods which is very commonly used. Rivest, Samir, and Edelman at MIT. And they said all we need to do is encrypt using basically a power of the message mod some number. So for example, you could use the key 3, 1, 187 where every message that you want to encrypt, you raise it to the power 3, n is a number, right? You raise it to power 3 and then take mod 187. This is just an example. And I'll show you how to get these numbers 3 and 187 in a minute. Okay? And to decrypt it, you take the encrypted message, raise it to the power 107 and take mod 187. Okay? So let's take an example here. Let's say the message is 5. To send it, I raise to the power 3 and I get 125, mod 187 is 125, so I just send 125. Right? The receiver takes 125, raises it to 107, mod 187. Now, 125 raised to 107, mod 187, how do you calculate that? So we went through all this mathematics before, and now you'll find the use for it. Is that you first write down this in binary, 107 in binary, you'll find that 107 is 64 plus 32 plus 8 plus 2 plus 1. So all you need is 125 raised to 1, then square it to get 2, then square it to get 4, and then square it to get 8, and then square it to get 16, and then square it to get 32, and square it. Every time you square it, you do mod 187. So all the numbers that you will deal with eventually are close to 187. Right? And so these are all small numbers, and then you multiply them one by one, and then you get whatever number you get. At the end, you will get a 5. Okay? So this is a lot of calculation, but if you know all the theorems that we have taught you so far, they will come out handy. Okay? And we'll see more uses of those theorems in the rest of this chapter. But first thing is how to raise something to a large power. You just keep squaring it and adding, squaring it and multiplying, squaring it and multiplying, right? So that's how you get it. Anyway, so if you do this, you will get 5. So the thing is, so in this case, one of the keys is 3, 187, which could be the private key, or public key, whatever it want to do, and other key is 107, 187. Okay, and you could use either one as one key and the other one as the other key. But obviously, once you make something public, you are not going to use it as private. So it doesn't matter which one you encrypt it with, you can decrypt with the other one, and which one you decrypt with, you can encrypt with the other one, so on and so forth. Okay, they're interchangeable. So the key differences from the symmetric key. Symmetric key means secret key. Symmetric key is same as secret key because you have the same key on both sides, the same algorithms on both sides. So basically, we use the same algorithm and same key for encryption and decryption. Here, one algorithm is used for encryption with a pair of key and one for decryption. So basically, I would say that I don't know whether I could call the algorithm is different. The keys are different, but algorithm is same. You just you just do the power and mod. Very simple. The sender and the receiver must share the algorithm and the key, right? Here the sender and the receiver must share only one of the keys and not the other. Then keys must be kept secret. Here one of the two keys must be kept secret. And then it must be impossible for somebody to get the other key. See, that's the thing. If somebody knows that your public key is 3, 187, they should not be able to calculate your decryption key. And that's what the whole world secrecy right now depends upon. That these keys are such large. Obviously, if somebody gave you 3, 187, you can easily calculate the other one. Okay, and I'll show you how to do that. But you can do that for small numbers. Right? For the numbers that we really use in practice, we use very large numbers. So nobody can do the calculations to calculate the other way around. Not with the compute power that we have today. Tomorrow it may be possible. Is it making sense to you? Yeah? Okay. You seem to be lost somewhere. All right. So, let me go back to this. So it must be impossible for somebody to decipher a message. Knowledge of the algorithm plus sample ciphertext must be insufficient. Somebody gave you the ciphertext and gave you the algorithm that I am using best, and here is my encrypted message. You should not be able to find out the key or the plain text. Similarly, algorithm is public here. In case of RSA, at least we know the algorithm. If I gave you the ciphertext and my public key, you should not be able to decrypt it. All right? So we already did this. So applications. You can use it for encryption and decryption, just like we saw in the example, but you can also do it for digital signatures. So we will actually have a whole chapter on digital signatures. And so nowadays you can sign documents. I don't know, how many people have signed documents online? Anybody has tried that? Okay. So you guys know that in Adobe Acrobat, they allow you to sign. That is a signature which is valid in the court. And we'll see how that is done. So basically nobody else can say, well, you cannot say that I didn't sign it because mathematically nobody else can do it. It is signed with your private key, and anybody can verify with your public key that, yeah, you signed it. Okay? And then the key exchange. So key exchange is, suppose you want to use secret key, how do you send the secret key there? Well, what you do is you use the public key method to send the secret key on the wire. Because basically, and that's mostly what we do actually. It turns out we don't really use public key for really encrypting messages because it is so complicated. Raising something with this large power is not easy. So we just do it to encrypt the secret key and send it. And then we use secret key after that. Secret key is much easier. I mean, you did the calculation for AES and, just to write those 4 numbers was so much work. But for computers, it's not that difficult, much easier, right, compared to public key. While the algorithm looks very simple, which is exponentiate and mod, but it requires a lot of work, okay? So there are other algorithms. RSA is one. Elliptic cryptography is also another one which is for public key. Diffie-Hellman is for public key and DSS, digital signature scheme. So all of these are there, and we will see most of these later. Some of these can be used for encryption, some of these can be used only for signature, some are used for key exchange. So for example, digital signature is designed for signature, not for key exchange. Diffie-Hellman is designed for key exchange, but not for signature. Elliptic key curve can be used for all 3, and RSA can be used for all 3. So right now, basically, RSA is the most common current method for public key, and elliptic key is coming. Elliptic curve is coming. So basically, those are the 2 methods. All right. So public key requirements. So Diffie and Hellman came up with this idea, and they said what we need is a trapdoor one-way function. This is a trapdoor one-way. Trapdoor. Nobody can figure out that there is a door there, but there is a door, and then once you get in, you can't get out kind of thing. It's a trapdoor, like a mouse trap or whatever, right? And so the function has the following property. You can easily calculate y is equal to fx, but you cannot calculate x is equal to f inverse of y. So you can calculate one way, but you cannot do the other way around. Okay, inverse is very difficult. It's like this. You can easily calculate exponentiation, but log is very difficult. We saw the log in the last class. Log is very difficult. So then we need function such that if given a key, we can calculate fx, and given a key, we can calculate the inverse. See, that's another thing, is that inverse is very difficult. I mean, if you don't know, if you don't know the right keys, but if you know the key, then it's very easy. Otherwise, it is infeasible. So basically, so he came up with this environment came up with this idea, but then RSA was the first one that found a practical scheme to do this. This whole thing about exponentiation, that example that I gave you, was the one that RSA came up with, and they came up with the idea that if we do this, then we can make it very difficult. Now, of course, you could do exhaustive search, trying all possible keys, but that is kind of not possible today because we use 512 bits, 1024 bits, 2000 bits keys, very large keys. So exhaustive is not even 56 bits. 56 would be too small for public key because the algorithm is very simple. In the private key, you saw that jumbling and shuffling and mixing and so on and so forth. So 56 bit gives you quite a bit of security. Here is just simple one operation, exponentiate and mod. So 56 bit key will not be useful at all. Okay? So we use large keys. 512 is kind of a small. 1024, government might use 4,000, 8,000 bits keys. But keys are too large. And then security relies on large enough difference in difficulty. So security is basically you cannot do the other way around, brute force. And the hard problem is known, but is made hard enough to be impractical to break. So basically we know the algorithm, we know everything, but we can't do the other way around. And it requires very large number. It's very slow. All right. So that is why, because it is so slow, that's why we use it only for exchanging the keys. So when you go on the web and you sign up and you say, okay, I'm going to give you my credit card number, they immediately change it to HTTPS, SSL. At that point, you have exchanged the keys. So you have a key, your computer has a key, and the other side has a key, so everything is encrypted with a secret key. But just before that operation, they do exchange the certificates, which are public key. Okay? So you exchange the public keys, and after that, with the public keys, you can exchange the key, secret key. Okay? And then the rest of the work is done using secret key. Everything makes sense so far? Okay. So here is how you construct the keys. Now, it is exponentiation in a Galois field over integers modulo a prime and takes log n. Exponentiation takes only log n raised to 3 operations. So it is very easy. But factoring requires e raised to log n operations. So factoring is very hard. Okay? So you take any text and you keep two numbers E and N and number D and N. E is for encryption and D is for decryption. Whenever you want to get a plain text M, you just do M raised to E mod N, that is your ciphertext. And whenever you want to decrypt it, you do ciphertext C raised to D mod N. Very simple so far, right? The main property is to get D, E, and N. What you have to do is you have to select two large primes P and Q such that P are not equal to Q, and then N is simply P times Q. You take two large primes. So that's why we learned that algorithm about just to find a large prime number. Remember, we had this algorithm in the last class where you have a large number, you know, determine whether it is a prime or not, that Miller algorithm. and that algorithm you just use to find the big prime. Okay, and then you take another big prime, multiply those two. That gives you n. Now, the key thing is that people given n cannot calculate P and Q. So your n will be in the public domain. You would have told the world that one of these is my private public key, so they know E and N. But from n, they cannot calculate P and Q. So you can. So you just do P times Q is n. Now we learn the quotient function. Now n is not prime, but Euler told us that phi n is equal to P minus 1. See, this is P is prime, so this is P minus 1, and Q is prime, this is Q minus 1. Product of those two is the quotient function. So anything, okay, anything raised by phi n will be equal to 1. Okay, anything raised, you take any number and raise it to phi n power mod n would be 1. That is one of the theorems we taught you, right? So, anyway, so select a relatively prime to phi. So select E relatively prime to phi. So you get this number and then choose a number which is relatively prime to phi, and that is your E, and select the inverse of E mod phi, and that is your D. So D times E mod phi is 1. When these conditions are satisfied, then x raised to ED. E is your one key and D is your other key, other half of the key. Okay? N is part of the key, by the way. So this would be, E times D would be something, some multiplier of phi plus 1. Okay? And so it will come out to be equal to x mod n. And so basically, you know, as you can see that you will be able to get these things. So basically, if you take C, put m raised to E here, you will get m is equal to m raised to ED mod n. You will get m back. So let's do an example that will make it more clear. So let's take two numbers. No, this is not an example. Example is coming on the next slide. I think this is just basically repeating what we said on the previous slide. So let's just do it one more time. D and E are such that they are inverse of each other. So D times E is 1, mod phi. Okay? D times E is 1 mod phi. So generally what we do is we take E to be very small number. So E could be 3, 5, something. Very simple like this. 2 raised to some power plus 1, because then we can get any message times raised to E very easily. So if it's just 3, E is 3, then raising something to power 3 just simply requires squaring it and multiplying it by itself. If it is 17, 2 raised to 16 plus 1, not 17, 2 raised to 16 plus 1, then you have to just kind of raise it by powers of 2 and then multiply it at the end. So this is basically simpler calculation. So we select E to be small, generally small and easy calculation. And then you have to find D. So anytime now you will be, in this chapter you will be needing lots of inverses. Very often you will need an inverse of something. Okay? So very first thing we taught in chapter 4, that algorithm, remember the table or algorithm to find the inverse, you will be using quite a bit in this chapter. And you should really get used to it. Because, you know, they will be coming very often in this chapter. Okay. In fact, yesterday, in the last class, we needed inverse, and I just said, you know, you can just do it by enumeration. But today I was doing another example, and if you did it by enumeration, you'll be doing it forever. So tabular would be much faster. So anyway, so you do the inverse, and once you get the inverse, then that is your other key. Generally, the rule is that don't select D to be a small number, because D is secret, and people will be trying all the possible numbers, and if a D is very small number, they would find it much faster than if D was large. E is public. And so E can be small. Okay? So don't select D equal to 3. Remember, what we want is the only property we need is that E should be relatively prime to 5. So generally 3 works out good because 3 is relatively prime maybe to 5. It happens in that case, we'll see in a minute. And then we'll say, okay, all right, let's select 3. So don't select 3, or not for the private one. And both D and N are 512-bit numbers, which is like 150-digit numbers. These are supposed to be big numbers. Okay? Obviously, we will use very simple, small numbers to see all this. So let's say we select 2 large primes, P and Q. So we selected 17 and 11. These are primes and large, right? At least for our brain right now. We don't have a computer to calculate. So these are large numbers. So P times Q is 187. So that is our N. All right? So we know one number at least N. We don't know the E and D. 11 times 17 is 187. So we calculate phi. Phi is P minus 1 times Q minus 1. Okay? So 16 times 10 is 160. So now we have to find a number which is relatively prime to 160. 160 is basically 32 times 5, 2 raised to 5 times 5. So if you don't select 2 and 5, you're okay. You can select 3, 7, any other numbers, right? So let's say we selected 7. Okay? Now this is your choice. You could have selected something else, but you selected 7. 7 is relatively prime to 160. Now you calculate D, which is inverse of 7. So we want to calculate D is inverse of 7 mod 160. And I'm telling you again and again, now you should just get that table in your brain so that you should do maybe 20 exercises at least so that you just so quick that you can calculate inverses. In this chapter, you will have to do lots of inverses. If you do that, by enumeration you can do it, but enumeration will take sometimes very large. Okay? So here is one method by enumeration. By enumeration is, you say, all right, if it has to be 1, product has to be D and E, product has to be 1, then it will be either 161 or 321 or 481 or 641. How do we get these numbers? We just take 160 times 2 plus 1. 160 times 3 plus 1, 160 times 4 plus 1, and so on and so forth. We keep writing. Now one of these is multiple of E, multiple of 7. So is 161 multiple of 7? No. 321 multiple of 7? No. And so on and so forth. Well, it turns out 161 is actually multiple of 7, so that's lucky. It says 161 is divisible by 7, giving D is equal to, okay, so this is very lucky that 161 is multiple of 7, so you will get 23 as the inverse. Okay? Once you got 23 as the inverse of 7, then your first key is 7, 187, second key is 23, 187. Now you can repeat the same exercise in your home when you are back by selecting some other value of E. This is not the only set of keys, right? You could have selected E equal to what? Can you give me another number for E?
11.
You could have selected E equal to 11. Well, 11 is relatively prime to 160, that's fine. You could have selected E equal to 3. Right? 3, you cannot select 5, you can select 7, you can select 11, you can select 13. All of these are relatively prime to 160. And for all of these values of E, there is a corresponding value of D. So you should do that also at your home when you're practicing. How quickly can you find the inverses? And I mean, this enumeration is just based upon luck. I mean, sometimes you get it very fast, and then you don't have to do the tabular. But the tabular method is guaranteed, because the tabular method within 3 or 4 steps you will find the inverse. So that's a fixed time algorithm. This enumeration could take forever. So for example, there's an example coming up. I was trying to do by enumeration. The answer was 14. Basically, we have to multiply it 14 times. I could not have gotten that by enumeration. I got it by tabular method. All right. So everybody understands how you get these numbers? How you get these keys? Okay. Take 2 primes, multiply them, that gives you n, then multiply -1. So p minus 1 times q minus 1 gives you this quotient function, quotient function for that n, and then you will select d and e, which are relatively prime, and they multiply to 1. All right. So basically the way it works is that you go to a certificate company and they will do all this calculation for you and give you your private key and public key. You will install it in your computer, and now you know your private key and public key. Whenever you go to buy something, you give your public key to the company that you're buying from, and they give you their public key, and then the rest of the calculation is done. Okay? So you're not going to generate these keys in your computer. It is already generated for you by some company. These are large numbers. Yeah.
So isn't that by definition means someone else has your private key and therefore you aren't the only one who can buy?
Yeah, that is true. So basically, sometimes these certificate companies have been broken in. Okay? If they're broken in, everybody who got this certificate from it, like if somebody broke into the license office, driver license office, I mean, they have all the data, so everybody's social security number. What are you going to do? So they have to be really protected. And basically, certificate is nothing but a signature which says that I signed that this is Raj Jain. So that's another thing, is that it's a certificate like you get a driver's license. If somebody forges a driver's license or somebody forges a passport, it should not be easy, right? If somebody broke into the passport office and made some passports, they're in trouble. And made your passport, let's say. Yes, so your observation is correct. Is that it's private, but yeah, certificate company knows it. All right, exponentiation. Now, there is something about the exponentiation. We already talked about how to do exponentiation. We will be doing a lot of it in this chapter. Is there 2 things we do. First of all, we learned that in the mod arithmetic, you can do it step by step, raised to the power square and the square and the square. But second thing you should know is, well, that's what basically it is here. But basically, there's another thing which you need to, that was in the last chapter. Remember, we said that quotient function is basically, if you take any number and raise to the power of quotient, then it is 1. So oftentimes you can remove those things, as we'll see in an example later on. You can take large powers and subtract out the quotient value. We'll see in a minute. But anyway, so this one simply says what we already did before, is that you do the squaring and then multiplication, squaring and multiplication. So first whatever power you want, you make it into binary, and then you calculate bit by bit by bit all the way to the end. And you can do it in Excel same way. This might be a good exercise to do in Excel as well, that you have A, and you want to raise it to power 107. So 125 raised to 107, mod 187. So how do you do it? You just go bit by bit. Right? Everybody knows this method, right? Basically, you have to just do squaring and multiplying. Because if you did if you try to do it in one step, if you wrote in the Excel that 125 raised to 107, it will be overflow. So that is not a good idea. And if you did it on a calculator, Well, even Excel it might do it, but this way it will do it in floating arithmetic, which is not a good idea. Floating arithmetic is not precise. So your message will already change if you do it in floating. It has to be done in integer. Okay? All right. Now, how do you optimize? There are three things you can do to optimize this calculation with big numbers. And listen carefully this. First thing you can do is that C raised to D, C is ciphertext raised to D mod N, is C raised to D mod PQ. Right? N is equal to PQ. So we learned the Chinese remainder theorem just for this purpose. Chinese remainder theorem says whenever you want to do mod operation, if you know the factors, then you can do it for each factor and then somehow combine them. Maybe I should open that chapter again. Last class, right? We did that, right? So P and Q. So what it says is you can do something C raised to D mod P and C raised to D mod Q. You can calculate these are all small numbers. P and Q are actually half size of N. In bits, I mean, in number of bits. So you can calculate these and then use the Chinese remainder theorem. Okay, to calculate the whole thing. Now in the Chinese remainder theorem, if you remember there were two factors right after the C raised to D mod P. You multiply it with Q times Q inverse mod P. Q inverse mod P can be calculated beforehand. And plus same thing you do with C raised to D mod Q times P and P inverse mod Q. So you can calculate P inverse mod Q. Maybe I should open that Chinese remainder theorem just to remind you. File open L08 whatever MNT Chinese remainder theorem. So here is Chinese remainder theorem. You see, if you have factor M1, M2, M3, you could have as many factors as you want. For each factor, you do this mod first, and then the rest of the factors. Now, in our public key, we only have two factors, P and Q. You cannot have any more, right? So P and Q. So this is capital M, which is the total thing, divided by little m is just the second number. P times Q divided by Q. P in this case would be Q, and this is just Q inverse. Okay, mod P. And then you use the second one, and then you add those two numbers. So that is the Chinese remainder theorem. All right. So going back to, so just remember this. You have to remember this formula, very important. Mod times the other number times the inverse of the other number. Okay, this should be just ingrained in your brain basically. The theorem is mod times the other number times the inverse of the other number. Okay, so we go back to this. You can store this beforehand. P inverse mod Q and Q inverse mod P, you can compute and store once. So then you don't have to calculate it every time. This doesn't change, right, with the message. And then since D is much bigger than P, right, could be, then you can use the other theorem we taught you that whenever you want to do mod P, the powers of P minus 1 will always be 1. Multiples of power of P minus 1 will always be 1. So we will see in a minute that basically when you want to do something mod P a raised to D, you can write down D as some multiple of P minus 1 plus R, and you can forget this big part and just do the R part. Euler's theorem. So we taught you Euler's theorem, and that's where we got into all this quotient function and other things, right? So I'm going to show you an example. So this example is in this handout that you have, a separate handout, black and white. And I added it after the original handout was printed. So just let's do carefully. And it was done last minute, like in the last 1 hour, so it might have some errors. but let's try to do this. So in our example that we just finished, the keys are 7, 187 and 23, 187, right? We calculated those two keys. So we first hand, this we call P and this we call Q. So P, this find out Q inverse mod P. There is already an error here. Q inverse mod, I already did a mistake. How did I get 11 here? Yeah, P is 11, okay, P is 11, Q is 17, sorry. So 17 inverse, okay, this is D and E, is how I'm getting confused, okay. So Q inverse mod P is 2. How do you get 2? I did the table, believe it or not, I did the table and I found it. Now that you know the number 2, you can easily verify it, that 17 times 2 is 34, which mod 11 is 1. Right? But to do this, you have to write that table and then do all the division and everything else, and within 4 lines you will get number 2. And this is where I got into trouble. I tried to do this by enumeration and couldn't do it until I did by the table. I got 14. 11 inverse mod 17 is 14. Okay? And now you can verify 11 times 14 and it will be 1 mod 17. Okay? So we did calculate this one. Now, whenever you want to do C raised to D mod PQ, this is the Chinese remainder theorem. We do C raised to D mod P times Q and then Q inverse, and then we C raised to D mod Q, then P and then P inverse. Okay, there is an error here. Mod P, this should be mod Q. Okay, the last thing should be mod Q. Please correct that. I need a paper. Just blank paper. Yeah. Okay, mod Q. Okay, so now let's calculate 101. Let's say the text is 101. So 101 raised to 23 mod 11. So right away, first of all, 100 raised to 23, I could have just I could have done 23 into binary, but before I do into binary, I realized that, look, 11 is a prime number. So we start with the theorem that whenever you have mod prime number, the power of 10 for any number would be, for 11, P minus 1 is a 10, 10th power would be 1. So 20th power is 1, so all we need to do is 3. So we subtract out P minus 1. Okay? And if you don't remember these theorems, you will be doing the calculation forever. And in the exam, there is only 1 hour, and lots of exponentiation to be done. Please remember these theorems, get used to using them as required. So this first simplification is, and this is what I wanted to say, was that any number raised to 10 is 1, right? For mod 11. 11 is a prime number. Whenever you have prime number, any number raised to P minus 1, where P is prime, is 1. Right? So, any number raised to 10 mod 11 is 1, and therefore 101 raised to 23, we don't have to worry about 20 part, we can just do 3. Now, for 3, now I will do binary. Basically, I did 3 equal to 1, 1. So I have 101 mod 11, which is 2. I can do this, right? 111 mod 2 is 2, and then square it, which is 4. Alright, so the total is 8. That was easy, right? No calculator required so far. Then 101 raised to now mod 17. So what do we do again? We subtract out 16 from here. Why 16? Because 17 is prime number, P minus 1 is 16, 17 minus 1 is 16. I'm left with 16 as subtract out, I am left with 7. Okay? Now I put 7 in binary, and then first I started with 101 mod 17, which turned out to be 16. Alright? Then I did 16 squared, and that turned out to be 1. And you should double check this because I just did it last minute quickly, okay? Turn out to 1, when I said square is 1, then then of course the fourth power is 1 as well, so I got 16. Okay, no calculator required so far. So all was done on paper, straight. You do need to know 16 square, which is 256. I mean, I suppose you all know that one, right? And you divide 256 by 17, and you get a 1. Alright, so 16. Now that we calculate these two numbers, we can do the Chinese remainder theorem, which says mod 11, 17 times the inverse of 17, which is 2, whole thing mod 11, and then this is mod this and that. So you put that number 8 times 34, and then 16 times 154. Basically, that is your 16 times, did I do it right? Well, let's see. This was 11, times 14, right? 11 times 14 is 154. Now, here another thing that you need to do is that when you're doing these mods, you don't have to multiply. You could just do the mod before multiplication. So I did that. So 34 became 1. Everybody getting that? 34 mod 11 is 1. So I didn't do multiplication, I just did the mod first. 154 became 1. Alright? Once you did that, then it is basically 8 plus 16 is 24. Alright, so you see, I mean, there are lots of calculations. If you try to do it without knowing those theorems, you're doing a lot of work. So the theorems are very handy. First of all, how do you do powers? By binary expansion, but before you do binary expansion, take out the basically the quotient function. So if it is a prime, then it is just p minus 1. If it is not a prime, then it is basically the factor. You take the prime factor, minus 1, minus 1, minus 1, right? So those powers can be removed. So for example, for 187, what is the quotient function? Anybody knows? For 187, what powers can be ignored? For the whole 187. 187 is what value? What is the factor? 11 times 17, right? So the quotient function is 10 times 16, 160. So you can, any number raised to 160 would be 1. Right? So if I ask you, what is some number raised to 161 mod 187? What do you have to do? You have to take out 160 and forget that, and then you are left with that number. If I ask you 321, again, 320, take it out by 160 times 2 is 320. Take that out, now you're left with 1. That's the only way you can do it. All right, moving on. RSA is computationally intense. The keys are generally very large, and the plain text should be smaller than the key length. See, that's another thing, is that your message, because you're doing mod, you cannot have a message which is bigger than the number itself. I mean, if you take some number and you mod 187, and if you add that 187 to that number and you take mod 187, you come out the same number. So the larger messages are no good. The message has to be less than 187 when you are doing mod 187. Make sense? So the message sizes are very small. If you have 1024-bit key, then your message should be less than 1024 bits. And so generally, and the encrypted text is the same size as the key length, and the remainder can be as big as n, right? So it could be 1024 bits. So generally used to encrypt secret keys. So that's the main use of this public key. And brute force search is kind of difficult. Timing attacks, actually some people figured it out that they will see how long does it take to decrypt, and then they can figure it out that as to how big is the key. But now you cannot do that because the algorithms are designed so they take the same time. Even if the calculation is easy, they will take the same time. They will just waste some time before decrypting. Mathematical attacks are based upon the difficulty of computing the factor of n. So if somebody can calculate the factorize those big numbers, then they're done. And then there is Fusion ciphertext attack, which is coming up next one, coming up in a slide. So some people can do that, and I will show you how that is broken. But factoring is very difficult. So in 1991, you could factor a 100-digit number in 7 years. MIP years, basically. What that means is if you had one MIP machine, it will take 7 years. But if you had a 7 MIP machine, it will take only 1 year. If you had 700 MIP machine, it will take 2 days. So that is MIP years. Everybody understands what is MIP? Million instructions per second, right? Like flops, nowadays we use flops, floating point instructions per second. So 110 will take 75 next year. So it's not, like large year in years. It is just basically we get a very powerful machine, and then we will do in some days. And this is the algorithm, and so on and so forth. So we are up to 155 to 200. Basically, 155 digits, which is 512 bits. So you won't really use this size key. Generally, we use bigger than 1024, and as the years go by, we just keep increasing. All right. So this is something wrong in your printed handout. Please change this thing. It says plain text attack. It is ciphertext attack. And so the red stuff is what I added in the slide after the handout was printed. So this one and this one. And this one. So it's chosen ciphertext attack. The idea is that if somebody could choose the ciphertext and send it to you and get the plain text, then they can figure out some ways they can get some information, basically. So here is basically that PU is public key. Given the public key and a message M, all we do is M raised to E mod N, right? If you do message M1 and then multiply this ciphertext with message M2, that would be basically encryption of M1 times M2. This is basically, right? So this is true. And so if you follow this formula, then so the encryption of 2M is simply 2 raised to E times PUM. So take any message, you get the ciphertext, and then multiply it by 2 raised to E, and send it, you will get 2M. So you can figure out, so basically what you can do is, you assume that E equal to 1, 2, 3, 4, 5, 6, 7, send it to the guy, and then come back. And then when you get the M that you wanted, then you know this is the value of E. Right? You are sending only a ciphertext. You don't know M at all. Right? You just do it by E and keep sending it until you find out you get M back. You want plain text M. Then you know E. Okay. So this is an attack. Now, so to fix this, the RSA came up with this algorithm, and the book actually has these two extra boxes which really confuse a lot. So I took this picture from Wikipedia, which is much simpler. Okay, this picture is from Wikipedia. The book picture has this other things, and I don't think they really need that. So and the rest of it is anyway. So it's standard. So what this book says is that if you want to send the message and some parameters, then you take those parameters and hash it and put it into the message and do all that. But I don't think we need to do all that. We just need to send a message. So here's the idea. Basically, the idea here is in this algorithm, padding algorithm, that if you have a message, if you just pad it with zeros, then that is not very secure, because because of this ciphertext attack, people could just multiply by 2, which is simply adding a 0, and somehow get advantage of the knowledge. So you don't pad with zeros. What you do is you pad with something which I will show in a minute. But basically, what you do is you take the message. Let's say message is less than the number of bits that you need. So you need k bits, and the message is k minus k naught minus k1. So this is the message size, and you add k1 zeros, and k zeros is a bits of something else. Okay, some random number. So there are total k bits. K0 bits from the random number, k1 zeros, and this many bits for the message. Total is how many bits? K bits. Because you have k0 bit random number, k1 bits of zeros, and these many bits of m. Right? The message itself is this big. So depending upon how big is the message, you can just change one of these numbers. Maybe R will remain fixed. I mean, the K0 may remain fixed, and if the bigger number and small number, you add 0, right? Then what they say is that you do two functions G and H. G is a hash function which takes K0 bits and puts out K minus K0 bits. And H is a hash function which takes K minus K0 bits and puts out K0 bits. Now everybody knows the hash function. Basically, when you want, and we will actually have secure hash in one of the chapters coming up. But insecure hash we probably have already learned in computer science somewhere, where you want to hash something, you do some division and things like that, and you come up with a number which is less than your table size. So you can go to the point to the table, right, entry. So this is what we are doing here. We are taking a number and then coming out with the answer which is K minus K0 bit. All right, and on this side it is just the opposite. So G and H are two hash functions, and the properties are simply that this one will take K0 bits and output K minus K0 bits, and this one will take K minus K0 bits and output K0 bits. Simple. So you take this, hash this with G and you output here, and you hash this with R and you output here, and you send this total thing to the other side. Alright? Now, with this padding, it turns out that you cannot do this kind of stuff where the message, if you multiply the message, this effect will not happen, because these things do not follow that property. So this one protects you. And other thing is that the receiver does not need to know R. Basically, receiver will take your Y, will take your X, use H function, and then Y, and then get R. And then they will take R and G function and then hash it and exclusive R it to get this. So basically they can get back to, so this is what you basically, this is what you encrypt and send, right? This is not encrypted yet. But instead of sending M, you send this. Encrypt it and send, right? So the other guy will decrypt it and then figure out what part is message, what part is random. Okay? So we are doing very secure padding. That's all we are doing. Very secure padding. And the padding is not just putting some bits at the end, but really taking the message, taking this random number and doing all this and getting this thing which is actually some number, and then we encrypt that. Okay, so this is called OAEP. optimal asymmetric encryption padding. Any question about this? That brings us to the end of this chapter. Public key encryption, so basically summary is uses two keys, one to encrypt and the other to decrypt. The keys are interchangeable. One key is public, the other is private. RSA uses exponentiation in GFN for large N, now Galois field N. So we learned about all those rings and fields and so on and so forth just to get here. For a large N. N is a product of two large primes, and that's why we learned the quotient functions, because then now we know the quotient function of N. And then we do the exponentiation with E and D, such that ED mod phi N is 1. So that is how you select the keys. Given the keys, both encryption and decryption are easy, but given one key, finding the other is hard. The message size should be less than the key size, so use large keys. Okay, those are the 5 key points.